Thanks everyone for coming. Today we're going to talk about link Floer homology. So this is the link Floer homology of Ozsvath and Szabo. So what we're going to be studying are links in S3. And there's a lot of different sort of variations of the construction of this object, but we're just going to focus on sort of the sort of most general version, which in my mind is sort of the simplest description. If I have a link in S3, well, what I can get is a complex that I'm just going to write CFL minus of the link. So I'm not really going to follow the normal convention. So this is, but what this gadget is it's a free finitely generated chain complex over the ring, and I'm also sort of abandoning normal convention. So if you've seen this before, you might have to adapt your the letters you write down for things, but you basically have it's a free finitely generated chain complex over a polynomial ring, and the number of variables, well, we have these guys, the W's, and we have the Z's. We have W variables and Z variables, and we have one for every component of the link. So if I have an n component link, I get two n variables. Okay, and so, oh, shoot. Okay, right, and so the first thing I wanted to talk about is just the general structure of this. This has a lot of structure. So the most basic thing to study are just sort of the gradings on this. It has a lot of different gradings that you can put down on it. There's what we call a Maslov or homological grading. So this is the homological grading. And it also has some extra gradings called the Alexander gradings. It has an n-component Alexander grading. So it's an n-component grading, and it takes values in a linking lattice. So the values of a generator, this takes values in this set. It looks a little funny. H of L, it's the product over it's the product over, so I equals 1 to n of, let's see, Z plus the linking number of L minus Li, or sorry, Li with the, sorry, here we go. So it's the product of Z plus the linking numbers of the ith component with the complement of the ith component divided by 2. So, e.g., for example, if I have a two-component link with linking number 1, it takes values in Z plus a half times Z plus a half. Okay, and the homological grading takes values in Z. So this is a Z valued. And we call this the Alexander grading. Okay. Now these variables have sort of predictable Alexander and Maslov gradings, or homological gradings. It's not so important the exact formulas, but we can write them down. They'll sort of appear later on. So the grading of the W variables, this is always minus 2. The grading of the Z variables is 0. And the ith Alexander grading, let's see, of Wj, this is minus the ith Alexander grading of Zj, and this is, I guess, minus 1 times the Kronecker delta function. Okay, so we have some fairly straightforward gradings that we can write down on these. So the actions, the module structure has some grading to it. It's not so important exactly what the formulas are, but just that there are formulas. Okay, and there's some additional structure. From sort of the relation with the three-manifold invariant, it becomes really natural to look at, to kind of think of the product of, we kind of define the product of wi and zi to be a variable we call ui. That becomes a very natural thing. Notice that the Alexander grading of ui is 0. These preserve Alexander grading, and they have Maslov grading -2. Okay, and it turns out that if you kind of study this invariant, if you study the link-Floer homology sort of carefully, you can actually show that all of the UIs are homotopic. So a fact is that all of the UIs are homotopic. So UI is homotopic to, well, the action of UI is homotopic to the action of UJ for all I and J. Right, it's a chain complex, I'm just saying that these are homotopic. Oh, and I guess I should also say, in the talk, F is always just Z mod 2 for me, so we're not going to worry about signs. Okay. So that's the basic invariant that we're going to study, or that's the basic, the basic structure of this invariant. Any questions? Okay, so today we're going to talk about L space lengths. I have to tell you what those are. All right, so definition. So L is an L space link. Well, L is an L space link. I'm going to give sort of an odd definition of it that just uses link-Floer homology, and I'll relate it to sort of more standard definition. But I'm going to say L is an L space link if the homology HFL minus, the homology of the version of link-Floer homology I wrote down, is torsion-free over f adjoin u. Well, remember we have these n u variables, but they all act the same on homology, so here I'm just saying where u is ui for some I. Okay? Like for any I. Because they all have the same action on homology. So just saying that it's torsion-free over this ring. So that's the definition. This is a little bit unusual definition. There's a sort of more standard definition that involves the three-manifold invariant, the Heegaard Floer three-manifold invariant. I'll state that, but I don't want to talk too much about it. This is actually sort of the condition that we're going to think about today. But this turns out to be equivalent, using what's called the large surgery theorem in Heegaard Floer homology, to another condition. So if I use what's called the large surgery formula, due to Ozsvath and Szabo, this turns out to be equivalent to the statement that Y is a Heegaard Floer, or sorry, what do I want to say? The surgery, let's say if we do Dane's surgery on the link, this is a Heegaard Floer L space for all, let's write it this way, just for all framings sufficiently large. Okay. I'm not going to talk too much about L spaces, even though the title involves L space link. This is really the condition I want to use. Maybe I'll just say in words, a three-manifold is a Heegaard Floer L space if it's a rational homology three-sphere, and its Heegaard Floer homology is as simple as possible, meaning that it's just a direct sum of different copies of the actual ring F adjoin U. That's not so important for the talk today, but this is maybe where the just a inkling of where the notation comes from. And here lambda is a framing on the link. I just take each, that means it's basically a collection of n framings, one for every link component, and I just take all of them very
Sorry?
Yeah.
I'm very confused by the first definition. So, I mean, if you take the positive trefoil, then HFK minus does have torsion. I mean, so what do you mean?
Yeah, so HFK minus, I think you're right. So I'm using sort of maybe a slightly different definition of, well, I said I was going to abandon the sort of standard notational convention. So typically what is called HFK minus, okay, we'll talk about an example and I'll explain what the cause of confusion. So an example would be the trefoil. Okay, so over this ring that I'm working with, this version of not Floer homology that I'm working with, which I'm probably, okay, so the confusion I think is the following. So I can think of this is a staircase complex. Oh, sorry, K is the right-handed trefoil, 2, 2, 3. So this is a staircase complex like this. Now the version of not Floer homology I think you're thinking of is, which is not unreasonable given that it's sort of the thing that's normally called CFK minus, and I'm abandoning normal conventions, is, so the normal thing is that you would call CFK minus would be the quotient of this by one of the variables. So I could say I could quotient by the z variable, for example. In which case I get the chain complex that looks like this. And if you take the homology of this, you do get torsion. You get one copy of F, and then you get F adjoint W, but this is not what I'm working with today. I want to work with the full version up here. And so let's think about what the homology is of this chain complex over this bigger ring. So this is traditionally what is called CFK minus, but I'm just writing CFK minus for the biggest thing that you could write down. But if you take the homology of this, you think about what does the homology of this guy look like, HFK minus. In this case, you have two, basically, you know, the homology is is generated by these two elements, and they satisfy the relation that W times this one is Z times this one. So I'm just going to indicate this with a picture. So I have these two generators, and this one, like I have these two generators here. If I multiply this one by W, I get the same thing as if I multiply this one by Z. And of course, there's more generators of homology. So if I can draw the homology like this, where each dot equals a copy of F. And the W action kind of moves to the right, and the Z action moves upwards. And if you think about this module, it's torsion-free. And in this case, the action of U, the product, W times Z, is just going to move me kind of diagonally here. Okay, does that answer your question? Okay, great. Any other questions? Okay, so maybe this is a good segue to sort of a general case of L-space knots, which is well understood by, is a very well understood setting.
Sorry, Ian, in this example, your homology is infinitely generated?
Yeah.
Okay.
Yeah, it's infinitely generated, yeah. So the homology, yeah, that's right. So the homology of this HFK minus is infinitely generated, but it's torsion-free of the HFK minus. Like, as an F adjoint, well, it depends on how what ring you want to say it's generated over. If you wanted to think of it as F adjoint U, then kind of it's generated by kind of the U action moves diagonally, so it's generated by kind of each of these generators here. If you want to think about it as being generated over F adjoint WZ, then it's finitely generated and it's just spanned by these two elements. Okay, so L-space knots. Let's just kind of talk about this more. So L-space knots. So this is a family studied by Ozsvath and Szabo, and it's actually kind of one of the earliest families of knots understood, or it's one of Ozsvath and Szabo's early results. So examples include the torus knots, so torus knots, for example. And actually all algebraic knots are L-space knots. This is due to Hedden. More generally, any knot which has an L-space surgery, I guess a positive L-space surgery is an L-space, let's say a lens space surgery will be an L-space knot. So torus knots, for example. Okay, so in algebraic knots, these are like iterated torus knots with, some restrictions on the the coefficients in the twisting as you do the iterated cabling construction. So in this case, CFK minus, or what I'm calling CFK minus, is always a staircase complex. All right, so we saw that sort of here. This is the invariant I'm looking at. It was sort of a not very complicated staircase. But more generally, what we'll get is we'll get a structure that looks like this. Okay, and so I'm going to have some generators along in two levels. We'll have W to the, let's say, alpha 1, Z to the alpha, let's say maybe beta 1 is how I'll label it, beta 1, W to the alpha 2, Z to the beta 2. So each of the edges is weighted by a monomial, and the monomials are just powers of W or Z. And they alternate between W and Z as I go along. So if the leftmost one is W to the alpha 1, the rightmost one will be Z to the, let's say, beta. Okay, how about that? Okay, so in general, the knot Floer complex is going to look like this. It's going to be a staircase. Each weight along each edge is a power of W or a power of Z. Okay, and now let's think about what the homology of this looks like. Well, it's going to look very similar to this picture here. I'm going to have one generator of homology for every generator downstairs. Let's just do another example. Let's not look at one that's too complicated. I'm just going to sort of make up an algebraic example and we'll study it a little bit more. Or maybe let's do, maybe let's not make one up. Let's just do T25. Think about this. So in this case, it's a staircase complex like this. And the homology, again, I have three generators like this. And again, we have a similar situation over here, but basically these three generators down here correspond to these guys here, and I have the relations just that W times this one is Z times this one, and then W times this one is Z times this one. And this is a Z and W. And so in general, what you end up with for any of these staircase complexes, you'll observe actually that they all kind of fit inside of just F adjoin WZ. So the homology of any staircase complex is going to actually naturally fit inside of F adjoin WZ. Basically, the point is I could just, if I just sort of filled in this kind of corner down here, I would actually just get a copy of F adjoin WZ. So if you think about what the homology is, it has a very simple form. The homology is actually what we call a monomial ideal. It's a monomial ideal inside of F adjoin WZ. And furthermore, we also have a bit stronger, if we look at the chain complex, we can actually see something very interesting here, which is that, well, the homology is generated by these generators downstairs, and there's kind of no homology in the top row. So there's a homology in the bottom that's generating the homology, but the homology in the top row, like the top row kind of just contributes relations. It doesn't contribute any homology. And so actually what you see is that CFK minus, this chain complex, is actually just a free resolution of the homology. So that gives us an important structural relation about, or that gives us an important sort of structural description of the not Floer complex. Any questions? Okay, so this is known for quite a while. This is one of the earlier results of Ozsvath and Szabo. They didn't really phrase it this way in terms of free resolutions and monomial ideals, but computing this sort of staircase complex is one of their earlier results. It's sort of well-used theorem in Heegaard Floer theory. And now we're going to move on to the point of the talk is, what about L-space links? Okay. Now, why would you care about L-space links? Well, this turns out to be a very important family of links. So, for example, algebraic links, all algebraic links, let's say in S3, algebraic links are L-space links. This is due to Gorski anemity. Okay, so, algebraic links are maybe the most, classical family of links that you could consider. I mean, maybe. They're certainly one of the most important families of links, or most, of basic families of links you could construct. Algebraic links are definitely one of the most important families of links. And actually, in Heegaard Floer theory, we don't really know that much about algebraic links. In Kovanov homology, we know more, at least in special cases. But actually, in Heegaard Floer theory, it wasn't actually even known what the link Floer complex of T and N was. Like one of the most basic sort of links you could write down. It was not really known what this was. And so what I can do, well, we can kind of, use this model, the L space not case, to kind of get a conjecture. And so the conjecture that I'll state is the following. This gives us a conjectural statement. Conjecture, and I'm just going to state it this way, that CFK minus of an L-space link, let's say L is an L-space link, is always a free resolution of its homology. Of, let's say, H of P minus. Okay. And I guess I'll report on some partial progress towards this theorem, at least some special cases where we know the theorem. Okay. All right. So here's a theorem. So some special cases of this theorem. Okay. So one is the classical one of Ozsvath and Szabo of knots. It's true for knots. So let's say true when. Okay. The second case is due to Borodzik, Liu and myself, which is for plumbed L-space links. And the third case, which is sort of work in progress. So in progress, this is with Darren Chen and Heegaard Zhou. Is when there's two components. Okay. And what are the techniques that go into these? Let's see. Maybe before I sort of describe, at least in some very sketchy terms, what the ideas are, maybe I'll just say another. Well, maybe I'll just sketch the ideas. So how do these go? Well, Okay, the theorem of Ozsvath and Szabo, how did they prove it when L equals 1? Well, this was basically just some homological algebra. That basically there's just not enough room for it to be anything but a free resolution of its homology. The case with plumbed L-space links, this uses a lattice version of link Floer homology, maybe plus a little bit of homological algebra. Basically, this uses some lattice homology argument. Basically, the idea is that there's this version of lattice homology which will compute the link Floer complex, and this sort of special thing in this case is that the lattice complex has this extra algebraic grading. It has this, it's this sort of cube-shaped complex. It has this sort of extra restriction on it. It has, in addition to all of these Maslov and Alexander gradings, it has sort of an extra algebraic grading. And that sort of forces, using some basic homological algebra, it sort of forces this, this structural result. And then this case that I'm working on with Darren, Chen, and Zhou, this again, it uses some homological algebra, kind of like, it's not sort of, basically we just kind of work hard doing some homological algebra and then we're able to prove this result. But sort of, these two cases don't really seem to generalize to three-component L-space links. It seems like our argument, I mean, you could try to say something using our argument here, but it doesn't really seem like it would generate links with more components. And sort of this plumbed case, the case where you have a plumbed link, will not generalize to the general case because there's no candidate for a lattice complex. The lattice complex is very special to the case of plumbed manifolds. And so we don't really know in general beyond this we don't really have an approach for the general case. I mean, you could try to bootstrap this case, but it doesn't seem like, I'm not as optimistic about that. Okay, so that's sort of the statement. So let's kind of discuss this and think about, okay, so there's some other interpretations of being a free resolution of your homology. There's sort of, let me say a little bit about that. So I guess in the talk we have the word formality which appears. So there's some equivalent definitions of this, or equivalent conditions to being a free resolution. So here's a little homological algebra, or just some very basic homological algebra. So if C is a chain, let's say C is a chain complex. Let's say we're going to work over this ring, the one that we're interested in today. But the same ideas work over general rings. But if I have some chain complex over here, you can consider the case where it's, being a free resolution, that's just saying that you have a homotopy equivalence as a chain complex with your homology. Viewed as a chain complex with, say, vanishing differential. Okay, this is equivalent to C being C a free resolution. Of its C is a free at least homotopy equivalent to a free resolution of its homology. This is not something that sort of generally happens. Typically, a chain complex will not be homotopy equivalent or quasi-isomorphic to its homology, but you can, in general, you can equip. So, in the general case, if you just have a chain complex, you can equip the homology with a structure of an A infinity module over this ring. Let's call this R. Over R, such that C is homotopy equivalent as an A infinity module to its homology equipped with these higher actions. Let's say A infinity module structure. And so these MJs are what I'm going to call the A infinity module structure, the A infinity action. So if you're not as familiar with this MJ, let's say maybe MJ plus 1 is a map. I guess I'll do a right module M tensor, let's say over F with R, and you tensor it J times. So it's a collection of maps like this where we have J copies of the ring. So M2 is just multiplication, M1 is the differential, and Mj plus 1 is sort of a collection. You need some higher actions on the module. These are like massive products. So in general, there's sort of this theory, homological perturbation theory, which just says that you can always, a chain complex might not be equivalent to its homology with just M2, but you can always sort of add some higher actions to it so that you do get an equivalence of A infinity modules. And basically, we say C is formal if we can take all of them 0, Mj equals 0 for all j not equal to 2. So we say it's formal if we can just take all of the Mj's to be 0. Except for M2, the sort of standard multiplication. And put it over here. Formality, however, is just actually turns out to be equivalent to just being a free resolution of your homology. So, so here's just a fact, is that formality, let's say C is formal, is basically the same as C as a free resolution. Well, at least homotopy equivalent to a free resolution of homology. Okay, so that's kind of where the word in the talk comes from. And that's actually sort of how we prove it. We actually kind of work in this world of A infinity modules, and this is really where the proofs kind of go through and how we think about things. But we state it in terms of just being a free resolution. Any questions? Okay, so then, and also kind of a consequence of all of this stuff, a consequence of the theorem is actually the ability to do computations for these lengths. So, computations, okay, so how do we do computations? Well, let's remember what I said at the beginning. If I have an L space length, if L is an L space length, basically the definition is just that the minus homology is isomorphic to a direct sum of many copies of f adjoin u, if I just take the homology. And how many direct sums? Well, actually, it's basically one copy of f adjoin u for every Alexander grading. So remember that u preserves the Alexander grading. So if you kind of sit and think about it for 5 minutes, you'll see that HFL minus actually sort of just decomposes as a direct sum of, well, something in every Alexander grading, and since it's torsion-free, basically that something turns out to be f adjoin, a single copy of f adjoin u. Okay, so, well, we can encode this, at least, well, so what is the structure you have here? You can think about what is the structure you have, what data actually does this encode, or how can you encode this structure? Well, each of these sort of towers will have a grading, and we encode the grading by what's called the H function. So we have what's called the H function, and this is just a function from the Alexander gradings to Z, and it's just given by HL of S. This is going to be like minus 1/2 times the maximum of the grading of an element where x is in HFL minus of L and it lies in Alexander grading S. So I'm kind of looking at this Alexander grading. I define the H function. There's some normalization, which isn't that important conceptually, but I pick the maximum grading of an element in the tower. For an L-space link, I could just stop here, but in general, you want to assume that X is FU non-torsion. For an L-space link, every non-zero element is non-torsion, but in general, we include this additional restriction. Okay, so what we observe, however, is that this H function, basically I'm just recording the gradings of the generator of each tower. And if you actually remember from the start of the talk, all of the module actions have a very predictable grading. So if I know, for example, the homological grading of a generator, and then I know the Alexander grading because it's just S. Well, actually, just that if you think about this for an L-space link, the entire module structure over F, all the W's and the Z's is just going to be encoded by this H function. Because they have predictable gradings, and so basically, in every grading, there's just one element, or at least at most one element. So if I have a non-zero element, that's kind of all that there is. So for L-space links, so if L is an L-space link, the F adjoin W1 Z1 module structure on the homology is determined by the H function. So if I know the H function, then I actually know the homology. And then, of course, if you use our theorem that says that for certain L-space links, such as plumbed L-space links or two-component L-space links, if you compute the H function, well, you get the homology module, then you can actually just get the full link Floer complex. So this gives you a technique, as long as you know the H function, to compute the link Floer complex. And it turns out that actually you can always compute this function HL for an L-space link. And that's due to Nemethy and Gorski, or Gorski-Nemethy. And basically, there's actually just a formula that you can write down. The formula is a little complicated. It's actually fairly practical to use. It's a little complicated, so if it is hard to parse, maybe it's not that important. It's maybe it's more important that just that there is a formula for it. But it's a sum over sublinks of L. And so then we have to sum over Alexander gradings in the lattice of the sublink. So I'm going to sum over all the Alexander gradings in the lattice of the sublink, and I want them to be, greater than or equal to, I won't tell you what this map is. There's some natural map between from HL to HL prime. So I won't tell you the formula. It's a pretty simple formula, but basically you just delete some of the components and then shift the remaining ones by some linking numbers. But I want to only sum over the Alexander gradings that are greater than or equal to in each component the projection of this sort of funny looking vector where I take S and then I add 1 to it. And what do I want to sum? Well, I want to sum the Euler characteristic. Well, I'm going to have of a different version of link Floer homology. Okay, and I'll tell you what this version is. I'm just going to kind of make up some terminology for it. I'm going to take the Euler characteristic of this guy, this is going to be the homology of a different version of link Floer of the link Floer complex where I quotient some variables. So let's say we take L and I quotient it by, z's, setting all of the z's to be equal to 0. And this is basically, this Euler characteristic, well, this isn't actually how we compute this. This is actually determined by the Alexander grading of the link. So this Euler characteristic is determined by the Alexander polynomial of the link. So determined by, I mean, basically this is just equal to the Alexander, suitable normalization of the Alexander polynomial. The multivariate Alexander polynomial of LP. I mean, basically, like what you do is you just take the Alexander polynomial of this length, the multivariate one, and this quantity, this Euler characteristic, is just the coefficient of that suitably normalized Alexander polynomial in the power s prime, if you sort of normalize things correctly. The point just being that basically this is actually just completely determined by the Alexander polynomials of the length. That's not too hard to compute. And so using our theorem, we can, for example, compute the link Floer complexes of algebraic links and all plumbed L-space links and also of two-component L-space links. So let's see. So, for example, two-component L-space links, there's a lot of these guys. For example, the Whitehead link with a suitable orientation is an L-space link, and there's a lot of Maser links, which are two-component L-space links. These come up a lot in Heegaard Floer theory for studying satellite operators. Okay, so I think what I want to do now is I just want to do some examples of what you kind of get when you run all this machinery. Okay, so maybe I'll talk about T and N. So here's a theorem. So this is, let's say we're going to do T, the link T and N. So this is with Borodzik and Liu. Okay, so T and N, let's consider just the homology module, which we know is kind of equivalent in some algebraic sense actually to the actual link Floer complex. Well, it actually has n generators. It's generated over this ring, over the W and Z's by n generators. It's good. There's T and N. It has n generators. That seems sort of morally satisfying. And it's subject to some slightly complicated, but not too complicated relations. What I want is I'm going to enforce the relation that a certain product of Wi's times xk is equal to a product of, I'll write exactly what these products are over, of some zi's for xk plus 1. So the relation, I'll tell you exactly what these are products over, but basically some product of wi's times xk is equal to some product of zi's times xk plus 1, and I need to tell you where the products are over. Okay, so this product is going to be, well, what I'm going to do is I'm going to look at k element subsets of 1 through n, and I'm going to take on this side, I'm going to look at I'm going to take the product over everything that is in, let's say, this set. So this has k elements. So here I'm taking the product over indices in ik, and here I'm going to take the product over indices not in ik. I mean, okay, maybe. And then we also have the relation that ui xk is uj xk. where we remember the UI is the product of Wi and Zi. Okay, so this is the module. This is the homology module, and as I've said, this kind of determines everything. So maybe just do some examples really quickly. So let's look at T22. Maybe before I do the examples, I'll just say this sort of builds on work. For example, Joan Licata studied T and N and came up with a series of conjectures, and then also Gorski and Hom computed, for example, they computed the H function, which was helpful for us. They computed the H function. Okay, so let's look at a few examples. So I'm going to look at T22, not a pretty simple link. Does the talk go till 50 after, or is it a 50-minute or an hour talk?
An hour.
Okay, great. Okay. Okay, so this has, actually this is quite simple. It just has 4 generators. So I'll write them A, B, C, and D. And, okay, this is not too complicated. Oh, maybe I'll use the same notation. X1 and X2. Right, let's see. And this is going to be W2. Right? So here you can see the homology is sort of spanned by the generators at the bottom. And you'll note that the relation that you get is that W1 X1 is equal to Z2 X2, and W2 X1 is Z1 X2. So that's kind of just like the simplest thing you could have here. You can also compute, this diagram, for example, is quite easy to compute just from a Heegaard. This complex is quite easy to compute for a Heegaard diagram of the link. Let's see, so I probably want to do, like this is a Heegaard link diagram. It's on a sphere, so I have W1, W2. This is going to be what, Z2, Z1. So this is a Heegaard link diagram. You can see there's 4 generators here, and if you count the bigons, you get this diagram. Okay, so then T33 was the next one. So these kind of, the module is pretty simple. In the module picture, we just add 1 generator every time we increase n. But actually, sort of, when you take a free resolution of this, it gets quite complicated pretty quickly. So that's why I planned ahead. So let's see. Hopefully we can do this really efficiently. So I have, hopefully, TNN. Okay, so this was T33. So it gets, and I forgot to say. Sorry, I guess this was kind of the old notation. The V's are what I'm calling Z's, and the U's, the script U's, are what I'm calling W. So sorry, we use slightly different notation here. But sorry, so these are like the W's, and the V's are the Z's. Sorry about that. So here we have the 3 generators, X1, X2, and X3. But then we have a lot more generators. And it turns out it's just pretty complicated to compute free resolutions of modules. Like this isn't a totally, this is like kind of an involved thing. It's algorithmic, but it's like, sort of computationally involved. But basically this is the homology as we keep going. At some point we did T44, and they get sort of more and more complicated as you let n, they get big very quickly as you let n increase. Okay, so I think that's, let's see, there we go, okay. All right, okay, so now I want to talk a little bit about, 10 minutes, I want to talk a little bit about 2-component L-space links. So this is kind of the general case or the plumbed case. These are the modules you get. And we can say a little bit more for 2-component L-space links. I probably won't say a whole lot. I'll just tell you kind of what the idea is very briefly. So for two-component links, so let's say two-component L-space links. So this is, as I mentioned, work with Heegaard, Zhou, and Darren Chen. Well, in this case, we're going to be looking at this link Floer complex. This is now over F adjoint W1, Z1, W2, Z2. So in general, we can write this as a free resolution of its homology, and that's fine. We can compute the homology using the H function. That turns out to sort of not be the most efficient way to think about it and to work with them. In general, for example, a free resolution will have this sort of algebraic grading, the resolution grading. Here's a 4-variable polynomial ring. You can have many levels. There's some bound that you get on the number of levels, but you can have many. And that gets a little complicated to work with. So the thing that we really want to work with actually is we need to just think about some way of understanding these algebraically. And really the thing we do is we just want to view it as sort of a bimodule over the product, or a bimodule. We can decompose this ring as, of course, a tensor product of two polynomial rings. And what we end up doing is we want to actually consider sort of a funny algebraic category. So what we're actually going to do is we're going to consider, so far we've considered things where we sort of have an action on, we've considered this sort of fully reduced version of homology where you just or of the complex where you just take homology. And then it's a module, it's no longer a free module. And then at other points in the talk we've considered sort of the free version of the link, or of the homology, where we have it's a free resolution, that in particular it's free, but it's big. And it turns out to understand the two-component L-space link, we want to consider sort of someplace halfway in between. So what we want to do is we want to consider a model, before I tell you what that's going to look like, just, a module over the tensor product of the rings. This is sort of the same, as a bimodule. A module over the tensor product of the rings. That's the same as a bimodule. That's a bimodule over these two rings. Okay, so what we want to do is we want to consider a model which is sort of free over one of them, which is free, or let's say at least projective. I mean, for our case, it's just going to be free over, let's say, F adjoint W2, Z2. Okay, and we actually sort of want to not consider sort of just modules. We want to consider actually sort of A infinity modules, as I mentioned earlier. That sort of is the actual world we work in. So what we do is we actually consider this sort of algebraic category of what we call DA modules. We consider an algebraic category. This is sort of work of Lipschitz, Ozsvath, and this is sort of introduced, or this organizational technique is work of Lipschitz, Ozsvath, and Thurston. And this is the category of DA modules. But these are sort of spaces M, and then you have these structure maps, which are sort of in between an A infinity action and a, let's say if I have two algebras, they have this sort of funny notation where you have a bimodule structure over the two algebras. So let's say A and B are algebras. We have a DA bimodule over these algebras. Well, that's the same as you have structure maps. It's kind of J copies of A, tensor M to M tensor B. And the tensor product for us is just kind of over the field, F. And then roughly speaking, if I just take the tensor product, M with B, this is sort of, this is like an A infinity module over A. and a free module, or let's say just maybe I'll say projective, it'll be free over B. That's what you want to think. So there's some sort of funny algebraic category, and this is really how we want to think about these two-component links. So what we want to do for two-component links is we want to consider a version of the link-Floer homology where we've taken this sort of free model and we've packaged it as a DA module. So we're going to do this sort of funny thing, and I'm just going to draw one example and then we'll kind of call it a day. But I'm just going to tell you what it looks like for the Whitehead link when you organize it like this. And, and then I'll just call it a day. Let's see, so, okay, so let's just do one example. Just to illustrate this, it may or may not make a lot of sense, but that's okay. So let's just do the Whitehead link. Okay, so this is a fun example. So in general, what we're going to have is we get, we're going to have sort of Z copies of staircase complexes, and then some maps between them. So in the middle, I have, let's say I have a, what do I want to say here? So this is kind of the middle piece. I have a differential. So, okay, so delta 1, 1, I'm going to say is the white one. So I have some differential in the middle. Okay, and now there's going to be a delta 2, 1. These should be W2 and Z2. Then in the middle, I'm going to have, and then I have a delta 2, 2, 2, 1, which is now where something on the left acts and something on the right is like emitted. Okay, and so I'll just kind of draw. So we have W1 tensor W2. I'll maybe explain what this means briefly. Here, this is going to be W1 Z2. This is Z1 W2. This is going to be Z1 W2. Z1 Z1 W1 W2. And then here we have W1 U2 Z1 1. Oh, and it keeps going. Maybe I won't. W1 U. So kind of as you go far in this direction, they kind of become the same thing. This pattern just repeats as you go to the right.
It should be Z1 Z1 or Z1 Z2 in the.
Oh yeah, that says Z2. Thanks. Yeah, Z2. And then here we have W1 1, and then going here we have a Z1 U2. And this kind of pattern just repeats to the right and the left. And this is, so delta 2, 2, 1, kind of you have an algebra element that comes in, and then there's an algebra element that comes out. If you haven't seen these before, you should just think of M tensor B as sort of free over the right, but like A infinity over the left algebra. And then finally, there is a delta 3, 1, going from here to here. I'm not going to write down the formula, but there's one delta 3, 1. So it's not too complicated. The A infinity-ness is not too complicated. You just have some differentials going from here to here. And of course, there's other actions of the products of Wi and Zi, but I'm just kind of writing down the actions of the sort of basic monomials here. And so this is sort of a way to organize these. So in the n equals 2 case this way, what is the point? Well, here you only have to work with staircase complexes. So free resolutions over this 2-variable polynomial ring. They're a little algebraically easier to work with than, say, taking resolutions over the 4-variable polynomial ring. That makes computing using them a lot easier. And this sort of diagram is sort of also easily read off from the H function. There's sort of a way to do it that's not too bad. And actually, the proof of formality, we work in this category of DA modules. So that's kind of why I introduced it as a different sort of a funny algebraic category to work in. But it's pretty useful because we're able to actually do this proof, this homological algebra proof for the two-component case using this category. Okay, that's all I want to say, so thanks for listening.
Okay, thank you. Are there any questions?
Yeah.
Can you use induction after you complete the two-component link, like being decomposing like six variable ring as tensor product of 4 and 2 and use previous results?
You can, yeah, you could try to do that. So like maybe have the A side be the 2n minus 2 variable one, and then the D side be the 2 variable one. But like, so when we do the proof, there's like we have to compute that some X group is 0. That's like,
Okay.
and so I don't know if that X group vanishes in general. Like there's some obstruction, in the n equals 2 case it vanishes. In the general case it's not clear, and maybe if somebody worked really hard they could show it, but it seems sort of hopeless. Like in the n equals 2 case there's just one thing you check, but in the general case there's sort of infinitely many, and it seems a little hopeless. But maybe a miracle happens. It just seems implausible to me that it would work.
Okay, any other questions? Okay, so if not, let's thanks Ian once more. Okay, and see you back here in hour and a half at 1:30. Sorry.
So one thing I can tell you for sure is that your life will change and you will never be the same again. In a very positive sense. I hope you enjoy it.
Connected some of them.
Did some 10th product of the
One good advice is try to keep track of the early months because
not any more than individual.
literally that's when babies grow the fastest. And if you forget to take pictures or to write memories about it, then it's very easy to forget that time even existed and how they looked. And it's always nice to look back and remember how much they've changed.
Censoring sort of, you have to like on the cosmology level,
all of that. I know everything about it.
When you go out to the left, there's a table. Hey!
that's right.
I know this shit.
There's a try to work on the presentation.
You have to, like, you tensor on the chain level.
Separately or
Yeah, I mean it happens.
I can write a homological integration K1 and K2 and then take a product.
Right. I mean, so the thing
That's
is,
one is
I plan
right, so
to
this is the
slide
category
because
of the Alexander polynomial, where it's like convert, where I said all the variables,
have to draw some
then you just tensor them together, because it's like a variety.
I guess you're gonna go Irving probably and not.
yes, mostly because those are the ones that have most sliced, but also try to present a bit
It's useful to take
of
tests.
Let's see how it goes.
They just,
I still haven't had much time to
algebraic invariant
work
combinations.
with the presentation. I haven't had time to
But
work.
still, like,
So far I'm trying to recycle from a previous presentation. That's why I also prefer to do slides.
Can we see those components are all fixed?
Not sure in the next 2 years. The next year probably or maybe I might apply. Let's see if algebra.
yeah, so that hasn't been, there should be some, there are probably techniques which like add components, but they're not.
Some engineering things, but then I think we should.
The common thing is like when you just have, you like cable a knot, and so you
It's
take
hard to
the,
say because
you keep the number of components the same. And it's sort of there's a
so-
complicated like relationship. It does sort of categorize interpolynomial thing. It's pretty complicated, like algebraically. There's some nice descriptions of it. I don't think there's, some of the stuff that to be pretty cool.
okay, so we can talk this.
Yeah, see you later.
I guess.
Yeah, we got my stuff.
Yeah, okay, I'll wait for you.
Hey, how you doing, Jesse? Great. How's Hamburg?
It's fine. I don't really have much to say about Hamburg because my position is research only. So it's like I'm not even doing any teaching.
Okay, well you're probably still enjoying the city.
Well, yeah, I'm pretty far away. But it's nice when I
You're enjoying something, right? Low teaching is good. You get a lot more time. Teaching can be good. Teaching interesting.
Till Wednesday evening.
Yeah, some teaching, yeah. Like calculus or whatever.
We're organized about 17 courses. I don't think I need more under.
Oh, that's great. It's great. Yeah.
If you can on Wednesday,
That's kind of
Even teaching like sort of a little more basic things, you can teaching just like an upper level, you know, it's a little more interesting at least, you're like remembering proof of like Gauss-Ray or something, you know. Whereas like if you're teaching
I wanted to verify that.
yeah.
I just wanted to know if you were alive, honestly.
Oh, nice. Yeah. Great.
you go for lunch now or?
Thank you guys, I just wanted to verify that you were okay.
Oh yeah, I'm sorry.
Does it have any old buildings?
Teaching calculus.
Okay.
Only this week. But I'm going back in the
Yeah. I taught that this semester. It was fun. That was the first time I taught. Yeah, it's fun because I realized I didn't really read this or whatever, you know, and I didn't. This is, you know, nothing that's that complicated. I mean, you could make it really complicated if you taught it really advanced, but just like, yeah, oh yeah, I think I bought that book to just have an extra thing, but then it wasn't very useful to be teaching. Maybe if I was teaching like something, it would be useful. Many of the proofs of like.
Find out that these were built like
I'm very proud of you.
Okay, yeah, I had good problems, but I didn't. We just used Atlas. Atlas, we were doing like I think one of the students that didn't know what a module was.
I noticed that.
Like, you know, we were like, we did pretty well. I mean, they all did well, but like, they didn't have, you know, they didn't have that much background. Like, they didn't know what a man was. Or like, they maybe they're like, oh yeah, I think I remember something. I just remind them what a manifold was. It was fun. But, no, it's good. Yeah. It was more work than I expected. I thought, because, you know, teaching, well, like teaching undergraduate classes, more than calculus. Hey, how you doing?
Yes, exactly.
You see?
Legal secretary.
They knew it.
He's coming in May, he's coming in May. Did you see? Accommodation. So I mentioned that thing which I was saying during the talk, maybe
After your talk?
the talk, I'll try and say what we were stuck and so on. Show some So I know, I'll present it to you.
Dig up.
No, I understand. Yeah. It's also a semester, too many things. Yeah. So we'll get back. And if I go back, then this small thing need to be sorted out.
Please go ahead. But I mean, I look at this paper, this whole paper.
Yeah.
I was thinking heavily, but I mean, I don't.
Yeah, but anyway, when it present, if you are there for the talk, that time maybe you will get more knowledge.
You will present it as well?
Yeah,
okay,
yeah,
right. Yeah, your talk is...
Tomorrow 11.
Yeah, I will. I have a class tomorrow at 2. So...
That's fine. 11 to 12 minutes. Maybe then you get some clarity of what it is.
Yeah, repeat again.
I think that people are living computers.
I don't know.
To jest moje pierwsze doświadczenie Noc in Poland 95. Paweł Klaczyk was sitting at the, not Paweł Klaczyk, it was Adam Sikora, was sitting at the end with computer or whatever. Then he didn't see on blackboard, he moved to first row and then his computer disappeared. It was 95, so it was in transition. Może teraz, bo ktoś zostawił. Z ekskursji. Żartowaliśmy, że robiliśmy zdjęcie, że może właśnie złodziej był na zdjęciu, ale...
Because I have no cash.
I took it this millennium, I took cash.
You took the... I don't know, maybe in midterm, yes.
No, it was used.
Ja właśnie tam zauważyłem jeszcze jedną rzecz, że na tych filmach na YouTubie